To understand what is that, let's revise in 2-3 minutes what we have done in the past session. So what we have done in the past session. First, the general structure. So let's write the general structure x, and then we have x of theta. This is what we want to know. What is this? And then we have the y hat, and then we have the loss function, which is also a function of theta. And the goal is to minimize this. To obtain this. Okay, because this is a function of theta. So this is a basic structure. Now, how do we solve this problem? So the way to solve this problem, so this is a structure, I would say. And we will solve this problem by minimizing this, which iterative minimization, gradient descent. We call it iterative minimization. So what do we do in iterative minimization? So gradient descent is defined as, so the goal is to find goal. What is the goal? Find theta star, the best theta, such that L theta is minimized. Okay, the loss is minimized. So geometrically, you can say that this is the loss, and if this is theta, and let's say this is the loss curve, the function, which is theta square, let's say. Geometrically, what we do is we start with a point, let's say here, let's call it x naught, and the goal is to, let's call it theta naught, because x-axis is theta naught, theta. The goal is to go here, theta star. So what do we do? And the goal is to follow the trajectory of the loss function L theta. So what we do is that wherever we are, we take the derivative of that. This is the derivative. The derivative is negative because it's in this direction. It's a negative axis because it's a negative. But we go to the opposite direction. Okay, in that same derivative direction. So this turns out to be, so how much opposite? So for example, if you go this much, you will be here. If you go this much, if you go this much, so how much? That will be the main question. So there is direction, and there is also, magnitude. So this magnitude is called the step size. I mean, of course, derivative has its own magnitude, but it's mostly for the direction. It's called step size, and how much you will go, or learning rate. And the direction is nothing but the minus of the derivative of loss theta at theta is equal to the theta I or n. Here it is theta 0, but in general it's theta n. So this is a basic idea. Theta n. So this is a basic idea, and mathematically it's written as, so for example, you will go here, theta 1, let's say. So theta n, or let's say that's defined as now n minus 1 to n. So theta n is nothing but the direction into the, like this direction, So theta n minus 1 minus this is the learning, right? And this is this times this is the step size, you can say how much you will go, times the direction. Direction is already in minus, so I'm just writing it together. And theta is equal to theta n minus 1. So this is the basic gradient descent. Usually we write derivative for gradient, for the derivative, but in this is in one dimension, 1D. What when we're in more than 1D, we write as this. Um, the reason is that in this case, in higher dimension, let's say the higher dimension is like this. Okay, this is the minimum. So what you do is that this is, let's say, theta star, and this is, let's say, sorry, theta star. Okay, and you're going, this is theta n minus 1. Let's say you want to go here, this is theta n in this direction, because you want to go to this, and this direction, right, towards this theta star. This is the minimum, like a cup. So this is now this direction, and step size is what, minus delta times this L at theta is equal to theta n minus 1. So this is nothing now but a vector. It's not in one direction, it's a vector now. Okay, so as you see here, so there are two things. One is, this is important. When I said this, actually the direction is also in the negative, the positive, towards the theta star, and that is the direction, and also how much. So that's important. So there is a direction and a step side. All of you got it, guys? So this is important. So that's why this is a vector now instead of a single number. Okay. So to revise, how is a, let's say, L theta 1, let's say there are two parameters, L theta 1, L theta 2 is theta 1 square, theta 2 square. So derivative of that is defined as like the derivative of the first element, derivative of the second element. 2 theta 1, 2 theta 2. Got it, guys? All good?
Yes, sir.
Any questions? Vivan, Anushka, Ahan said already. So this is the basic idea. Okay. So this is the basic idea. So let me. So let's call it introduction or revision. So next part is, so how we'll do? So initially we will do revision, and then we will go ahead to do on small examples like linear regression, logistic, and then we will go to deep learning. Okay. So let's try it on linear regression. So first we'll do linear regression. Now you may ask that, there are two aspects to it. One is you can literally write down. So there are two ways to calculate. You can literally, okay, before I say that, let's remind ourselves that what was the whole idea. We can write the linear regression as, so remember the input was, let's do simple linear regression. Like let's say yi is equal to w xi plus b. Okay. And even if you write this, if this is the yi, the entire, understand this very carefully. Um, this you can write as yi is equal to w comma b times x I comma 1. Okay. Or you can also write as 1 comma xi in a different way. This is dot product. Okay. P comma w. So the yi hat, rather not yi, the yi hat is this, the predicted. And the loss, which is a function of w and b, is nothing but yi minus yi hat whole square, right? Which turns out to be, because yi is constant, you know yi is constant, xi and yi are given. So they are constant, they are data sets. And w and b are unknown. These are parameters, theta. So yi minus, you can say wxi plus. So this is for the I at the data point. So loss for I at the data point, whole square, right? So how is the final loss defined? The final loss is nothing but, if you remember, it's nothing but the average of n data points are let's there, average of individual losses. So you may say that why are we not doing individual the whole loss? The reason is this. The reason is derivative is linear, like is invariantly, like doesn't change to, or rather, okay, is additive. What do I mean by that? I mean that if I do this, so let's, there's a function f of theta is equal to f1 theta plus f2 of theta, then derivative of f is nothing but derivative of f1 plus derivative of f2. It's linear. Okay, it's called additive, linear operator. So here in this case, if you observe, del w will be nothing but 1 by n summation of 1 to n, the individual derivatives, del li w p w. Okay. In fact, now let's use, so let's assume that, theta is this. Theta is equal to w comma b. Let's assume that now here. So if you now do del L, the entire L, so we can also write this as loss of theta is 1 by n summation of individual losses. I just replaced w comma b as theta. So del L theta, the derivative at theta of loss is nothing but 1 by n summation of 1 by del L theta Li. So what do we learn from here? The learn from here is that if we find just if I find just loss gradient or loss gradient for one data point, the formula we can add them up. The formula. So we do not need to find individual formulas. We can just do it for one and then add it up. So this is useful, right? So let's coming back here. We have got Li of w comma b as a function of yi minus wxi. So here it will be this together actually. Minus b whole square. Okay. And you can find it. You can find it that so instead of calculating the whole thing, if you observe, it's a composition of two things. One is yi minus this, and then there's a composition of square to the power. So this is the beauty of it, that instead of finding the entire expression, we can use the idea of composition. So as if you remember, it's deep learning or anything in deep learning, the function is compositions. It was the whole idea the deep learning was based on, that it should be simple, right? So it's composition of simple functions like linear, ReLU, all simple activation functions, okay, square, very simple functions, etc., etc. Okay, the loss function is also simple, logarithmic or loss. Okay, so it's a fundamental idea is its composition of multiple functions. So the final loss is composition of multiple functions. In this case, you can see it's composition of this and squaring. So we can also write this as, so the whole idea is theta, because we want to find the derivative with theta, and so you can write this as yi minus w xi minus b. Then the square comes up, whole square, this is to the power square, and then the loss. So as you know, for composition of such, finding the derivative of such loss function, you have to use something called chain rule. So what does chain rule say? It says that if a function L theta is a composition of this, like let's take two examples, then the derivative of this by this will be nothing but first, which is outside, take that. So derivative of f1 with respect to what's inside. Okay, so yeah, derivative of f1 with respect to this f2, because f1 is a function of f1 is a function of f2, like the input of f1 is f2 times derivative of f2 with respect to them, because f2 now is a function of theta. Okay, so in some sense they're cancelled out, but do not take it like this is how you remember it, but do not take it for granted. Yes, there is a meaning why it's cancelling out, There's geometric meaning. Let's not go into there. But for you helping you understand, you can think of it like generally as if let's say loss function is, so let's write it like this. Simple. F1 composition of F2, then composition of F3. It's not multiplication, it's composition. Let's write like this. It's not multiplication. F4 dot composition of Fk or L, then dl d theta will be first df1 divided by d of all f2 composition of all of them, fl, then times, then this will go up, d of f2 of composition of till fl by d of starting f3 composition of fl. So it will carry on till the last term will be d of fl by d theta. So it's like, for example, for 3 it will be df divided by df1 f2 f3 times df2 f3 divided by df3 times df3 divided by d theta. Okay. Now let's take an example of for the square. So if you observe loss in that case, if we assume f compose f2 of theta, the first one here, if you remember, f1 of x outside is square and f2 of theta is yi minus w xi minus b. So del L del theta will be df1 by df2. So you can df, so essentially it means that f1 is a function of f2. So it means f1 of f2 is nothing but f2 squared, which is essentially happening. So df1, so f1 is f2 squared times df2 by theta, because you can see f2 is a function of theta. So f1 is f2 squared, so it will be 2f1 to f2 times the derivative of this. So here, okay, so here you can understand it, you have to divide by respect to theta is not a function here, so we have to find in terms of w. So let's do it in terms of w. Now in terms of w, you can see just minus x1 will be there because others are constant. So minus x1. Okay. Now we have to do also dl by db. Again, the same thing, df1 by df2, which will give 2f2. So of course, first of all, you have to write it in terms of w finally, or w and constant. So f2 is nothing but, so 2 times this yi minus wxi minus b times minus x1. Okay. And here the same thing, df1 by df2 divided by db, which will turn out to be 2f2 minus, now you can see minus b, you are taking the derivative with respect to b, so it comes out to be minus 1. So it will be 2 times yi minus into minus 1. So this is the derivative of with respect to, finally with respect to theta. Did you understand, guys? Vivan, Anushka.
Yes, sir.
So we are getting the derivative of both. So now if you do del L theta, it will be nothing but dl by dw comma dl by db, which will be this 2 times yi minus wxi minus b minus 2 times x1 comma minus 2 times yi minus w xi minus b. This is how it looks like for simple linear regression. But you can understand, so this is for just simple linear regression, you have to work so much. Now let's go to multiple linear regression. So if you remember last day we discussed that it can be, we should express it in terms of matrices. So if you remember, it was yi is equal to b plus w1 x1 plus w2 x2 plus dot 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 yi hat dot dot wk xk, and we wrote this as 1 comma x1 comma x2 dot dot xk times this b comma w1 comma w2 dot dot wk. Let's call this theta, and let's call this x transpose. Transpose means it's because, yeah, so it's called x transpose theta. Transpose is a matrix operation. So x ideally looks like this. So x ideally looks like this, but we are transposing it to make it to look like this. Otherwise, the dimension will not match for matrix multiplication. So yi hat is can be written interestingly as this simple way. Okay. Xi. Now what? Now let's try to find now the thing is that the loss function L of theta is y hat minus yi square naturally, or let's say yi minus y hat square. It's the same, is yi minus xi transpose theta whole square. Now the thing is that we are trying to write it in terms of matrices. So what we'll do is that if any vector, let's say a is a single number, it's a 1 cross 1, a transpose is also a, because it's also 1 cross 1, it's the same number. So when we write a square, it's same as a is a single number. We can also write a transpose because a times a. So what we'll do, we will do similar things here. Yi minus this transpose yi minus this. Remember, these are all single numbers. So we can get to an equation. Yi transpose yi minus twice yi transpose xi transpose theta plus let's write it properly. So yi minus xi transpose theta, this is L theta, L theta ith loss is yi transpose yi. Now if you add it, you will see both are like yi transpose xi transpose this. So it will be two of them. One is this, another is this. and both have minus, so it will be yi transpose xi transpose theta plus the plus 1. So xi transpose theta transpose xi transpose theta. So you will see this turns out to be theta transpose xi. So theta transpose, so when it's AB transpose is nothing but BA transpose, B transpose, A transpose. So these are rules you need to remember, and you don't need to remember, you can use the internet out there to check it out. So this becomes B transpose this times this plus theta transpose xi transpose theta. So this turns out to final loss function. So let me write it down properly. Li theta is yi transpose yi minus twice yi transpose xi transpose theta plus theta transpose xi transpose theta. Okay, so it turns out in terms of that vector theta, and it's very important because now such like similar to the results of, we can use matrix derivatives. They're matrix derivatives just like we have individual single variate derivatives. Okay, so if you do matrix derivatives, you will see that del Li by del theta, or it's not del now, it's del L theta Li theta. Now this is not dependent on theta, so this gets cancelled. So we have, now this is dependent on theta. So we have to now remember or check that. So first of all, theta is, so how to remember these things? Theta is k plus 1 dimension, okay, comma 1. K plus 1 rows 1. So the output of theta, del theta, the gradient should also be the same. Remember that. So that's how you, because often, so essentially often you forget whether it will be, so for example, it's minus 2 some vector here, yi transpose xi transpose times theta. Oh, yeah, there is a small problem here. The problem is, I probably, yeah, so this xi is not same as this xi because, yeah, there's a small notational error. So these are dimensional xis, okay? So let's call it above. Yeah, there is a notational error. So this is the data point xi. And this is the dimension. So you can now see that, so you can find out what will be this. Yi is a single number, remember that. So this is nothing but the dimension of xi transpose. Okay, minus 2 times. So essentially, what is like some constant times theta divided by theta, it will be just constant, right? But the constant dimension should be the same as the dimension of theta. And theta is k plus 1 comma 1. So you have to make sure. So if you just say that it will be minus 2 yi transpose xi transpose, because it's just a constant of this, it will be wrong because this is now, if you remember, xi transpose is this, it's 1 comma k plus 1 dimension. So you have to take a transpose of that to make the dimension similar to theta. So it will be another transpose of that. Did you understand this, guys? You understand the idea of what I'm saying? Yeah, I do not expect you to do everything out here fully. Just try to understand the idea, remind yourself. Okay, so that when you if you use GPT to understand or solve, you at least can understand, okay, this is the logic. Because I don't expect you to do all of this. I want to show you that how it's done. And it's important to understand how people think. So this will now, it will be k plus 1 comma 1, dimension 1. And here it has another formula. So just give me a minute. So if you take the one dimensional version of this, it will be theta times a constant times a theta. So it will be a theta square, right? If you see, check the one dimension. If you take the derivative of this with respect to theta, it will be 2a times theta, right? Similarly here, if you take the derivative of it, it will be similar to that. It will be theta, and in the beginning it will be something like this, but you have to check the dimension. So xi is k plus 1. Sorry. Yeah. K plus 1, comma 1 dimension. Xi transpose is 1, comma k plus 1. So this entire thing is k plus 1, comma k plus 1. And theta is k plus 1, comma 1. So the output will be k plus 1, comma 1. So it's fine. Do you understand, guys? So to check the dimension change, what will be the final dimension? Okay. So now the dimension is same as, total dimension is same as theta. So we get minus of 2 yi, because understand that if you its dimension is not same as theta, you cannot do this step, because you are moving in the theta dimension. You're doing theta minus this del, so this both of them should have the same dimension. It cannot be like 2 comma 1 and 1 comma 2 subtract. You cannot do that. So it will be 2 comma 1 comma 2 minus 2 comma 1 dimension wise. So that's why it's very important. There will be a few homeworks actually based on that. So now this will be, if you do the change the transpose, it will be again AB transpose is B transpose A transpose. It will be xi and then yi plus xi transpose comma theta. Okay. So this is the L theta. Now since you found this, you can now apply it. So you can, so now how do you find the gradient descent? You apply initialize theta naught with with a good guess or random. Then you know the del L theta. So you build a function of u def gradient of theta. You define the function. And then you update theta n as theta n minus 1 times minus the gradient of theta at n minus 1 times this learning rate. This will update to theta n, and then you build a for loop. So I'm trying to give you a pseudocode because next day we will be coding it out. So this is a pseudocode. Okay, for loop till it converges. All of you understood this, guys? Fully? The whole process, Anushka, Han? You have any questions?
No, sir.
So we have learned now how the entire process happens for multiple linear regression. We have learned how the entire process happens for simple linear regression here. Let's call it simple. Okay. And we have seen how things happen for gradient descent and the code structure. Okay. So let's mark the important thing, chain rule. So this is another important thing. Okay. And another important idea is this. So this is the important idea, rather additivity. Okay. So we have now learned how to find the how. This is an example. So similarly, you can do it for logistic regression. So in logistic regression, if you remember, let's directly calculate the y hat in terms of matrices. So yi hat, the same, this x transpose theta, xi transpose theta, same, but there is a probability function on it. Okay. Which we call softmax. We can also call it sigma if it's for binary. For binary. And then loss of theta will be if you remember yi times 1 minus y hat, sorry, minus of logarithm, sorry, minus of yi times logarithm of 1 minus y hat minus of, so the entire thing is actually within brackets. So plus 1 minus yi logarithm of 1 minus, what am I doing? Sorry, yi hat. One minus y hat. So we have to take the derivative of this now. So you can see now the different layers. So initially it was xi, then you got this xi transpose theta, then you got this sigma, okay, and then you got this loss. So at this point the output is called yi hat, at this point o1 hat, okay. So you can see this is the first composition, f1. This is the second composition, f2. Essentially this is the f2, this is the f1, and this is the f3. So loss is nothing but now f3 of okay, so this is an issue. We can do it otherwise because we defined it like that. So see, this is f1, this is f2, this is f3 because you are going backward. That's why it's called backpropagation. Okay, you're going backward because this is being applied first. The most outside one will be this f1, then f2, then f3. Sorry, this is f1, this is f2, this is f3. of theta. You can see the theta is actually in the deepest layer. So you are actually propagating to find that you're actually finding the loss backwards. You're propagating backwards. So this is the basic idea of that's why it's called back propagation. Did you understand this, guys?
Yes, sir.
Others? Okay. Here's F1, F2. So let's now understand this. So this is very super important. Let me mark it out. F1, F2, F3, F1, 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 F2, F3. So the loss is the F. So see, the loss is the F1, the sigma is the F2, and then F3. So similarly, you can find the derivative of all of them. Okay, the goal is to find the derivative of all of them one by one. So for example, here, if you do, yeah, so here if you observe that loss is a function of y hat. So let's assume y hat, if you observe that, let's call OI, or let's call O to be xi theta, or rather F3. Let's define F3. F2 is sigma of F3, right? Which is also y hat, yi hat. And then F3, sorry, F1 is now is the loss of I mean, this is a wrong statement to say it's F3. It's sigma x. So this is a bit of wrong statement. So F3 is, so F3, so write everything in terms of x, or let's say some other function a. F3 of a, where the input is that, is nothing but a transpose theta. Or sorry, you see, a is actually should be theta. So you have to be very careful here. Xi transpose a is actually theta. Okay. F2 of some a here. F2 of a is sigma of a, which is nothing but, if you remember, e to the power a by e to the power 1 plus. Okay. And F3 of a is, of the yi is constant. So what is inputting? Yi hat is inputted, right? So it will be minus of yi ln of a plus yi 1 minus yi ln of 1 minus a. In this case, a is equal to yi hat. In this case, a is equal to xi a, xi theta. So do you see the composition here, guys? Do you understand the levels, the depth? So now the loss, final loss is nothing but what? F1 of, sorry, this will be F1. I make this mistake over and over again. F1 of A, which is A here is its input is F2, and F2's input is F3. And F3's input is actually theta. Do you see the point, guys?
Yes.
So to find out del L, del theta, symbolically, you do not need to find out the derivative of all this entire thing. To find out, essentially, you need three things: del F1, del A, okay, del F2, del A, and del F3, del A, because both of them are functions of A. But in this case, A should be yi hat, where it's evaluated. That should be yi hat. In this case, A should be evaluated at this xi transpose A. And in this case, this should be evaluated at theta, or rather theta n minus 1, whatever the theta value is. So you see this entire this entire loss is just dependent on derivatives of these three easy functions, because it's compositions of derivatives of easy functions. Okay, so this is a basic idea. It's a derivative of easy functions, but you have to evaluate at different points. Evaluate at different points. This is very important. So in this case, you can think it like this. Understand, this is very interesting. So I am not finding the derivative of here. You can easily find out the derivative. You can use a derivative calculator. But the core idea is important. So revision, so to revise, this is the structure. You can think of xi transpose here, theta, as this theta input. And then there is a sigma. And then there is a loss. This theta is constant here. This theta is the only variable. All of them are constant. So let's call it not xi, but x. Now, of course, you have y here, the y input here. But when we are doing del L theta, what we're doing is that we are doing let's call it F1, F2, and this is F3. So we are doing delta F2 of F1 times delta, not times, okay, you can say times. You have to understand what it's doing. Delta F3 of F2, or what I'm saying is that delta F1 evaluated at input as whatever the F2 output is, times delta F2 of F3 evaluated at the F3 output, times delta F3 of theta. So what's happening is that you calculate this backward, the value is going backward, and then finally it's updating here. Now once you find this, then you can update the theta. Then you update, okay, theta n is equal to theta n minus 1 minus of this del theta is equal to theta n minus 1. So this is a step by step, because in deep neural networks there are a lot of layers. So let's say there are hundreds of layers. So you have to have an iterative algorithm to calculate this. So in general, let's say it's like this: x f1, there can be theta 1. If you remember, now in general for deep learning, what is happening? To revise, in general for deep learning, what's happening is, if you remember, the input is x, then there is a, if you remember, the input dimension is x, then there is a w transpose x, sorry, x transpose w, right? If you remember, the first, this is x, then there's a x transpose w to get the next one. And it can be, it's just not one single, so it can be a matrix also, because the output can be a multidimensional. So it's w transpose or x transpose w. It can be multi-dimensional. In this case, it was k plus 1 comma 1, but it can, if it's multiple outputs, it will be k plus 1 comma multi-dimensional, right? So it's m cross n, or k plus 1 comma n. And then there is a non-linear function, understand that. Let's go to the very basics. It's a non-linear function, it's called activation. That's the first layer. And then let's call, since it's the first one, W1, then there is W2. So although A1 and A2 are same, but you can keep it different. And then there is, so let's write it in a simpler way. In general X, then X W1, then A1, then X W2, then A2, then X W. Sorry, what am I doing? I mean, you can say that. So it's not X input here. You can say that. You can just say what is being up, because understand here the X is not this. X is A of X transpose W. So what we can do is that we can say the layers. What are the operations happening? So instead of this, it's not X transpose, not X, but A1 of X W1. What is the output of this first layer? Right. So we can just define the F1, because that only matters back in backpropagation. In only the F1 matters. What is the function that matters, right? The individual functions. So we therefore define those as layers. X, then we call it the W1 layer. Okay. When I say the W1 layer, it means essentially X transpose W1 as a function. Okay. And then the A function. And then again the W2 function, the layer. So we call it layer. But every layer is correspondingly a function. Is a simple function. And then A2, then W3, then A3. It can continue like this, right? This is finally, it continues, and then finally some output comes. And there will be another. So for example, the softmax layer is also an activation kind of function. So what happens is that each of them turns out to be a function. You will see when we code, it actually is done that way. So there's an input X, there is layer 1, there is layer 2, there is layer 3, there is layer 4. We have to actually define the layer by hand. Layer 4, layer 5, like this. And then you have to propagate it directly. In the back end, essentially, at the final step, we calculate the loss. Let's say we have the layer n, and then finally the loss comes up. Okay, let's say the air, this is the loss output. Not the loss, the output of this is the loss, L theta. Now understand one thing, every layer may have a theta. So for example, this W is a parameter here. So it's theta 1 here, theta 3 here. Every layer may not have a parameter. Okay, understand this. For example, activation, no parameters. But this W is a parameter in itself. All of you get it, guys? So it may not have a parameter, right? So let's now understand in this very case, how do you backpropagate? So let's take a simple example. Let's say X is W1, activation, W2, activation 2, then loss. 3 layers. Okay. And here the theta, the W1 is the parameter. Let's call it theta 1 is a parameter. Theta 3. So let's see how we'll calculate the loss. This L, So the final loss is what? Final loss is L of A2 of W2 of. So let's call it something different. Let's call it the layer 1, H1, the hidden one, hidden layer. It has a corresponding hidden, and then sorry, it will be from outside H2, and then A1, and then H1, and then uh, I did it wrong. You see, you start from back propagation. So first, this L. L is already a function of theta. What am I doing? Wait. I did it right actually. First L, and then inside of that is A2, inside of that is H2, inside of that is A1, inside of that is H1, and inside of that is this. Okay. But understand, every layer has theta 1 and theta 2, like some of the layers. So how do you find? So when you are doing the derivative, you have to do, for theta 1, you have to do the update separately. So for theta 1, there is a n, for the theta 1, the layer 1, n minus 1 minus del of theta 1 L at theta 1 is equal to theta 1 of n minus 1. So this theta 1 is not same as the iterative, but the layer theta 1. Theta 2 of n will have this. Okay, two different thetas are there, which was not present in linear regression or logistic regression. That's why I am trying to teach you something new here. So there are two different levels. So what we do is that we stop at this level and just propagate. So essentially you see that for this theta 2, you just need this two, this one and this one. For theta 1, you need all the four. So that's why it's again called back propagation. So you come here, and you calculate. Okay. So let's understand what's happening here a bit mathematically, just abstractly. Okay. So let's just take what will be for theta 1, this one, del theta 1 of loss. So what's happening? If you remember, it will be L dash, the derivative of that. But understand the input will be this A2, output of A2. Or we can call it del L A1, A2 times del A2 by del H2 with respect to H2 times del H2 divided by del theta 2. Once you do this, you get the theta 2 update. Okay. But you will not do this step for theta 1. Let's see what we will do for theta 2. Understand, it's happening X to H1 to A1 to H2 to A2 to L. Here there is theta 2, here there is theta 1. Just to revise. So for this, you do this, this, and this for this entire thing. And you save it up. For this, again, you do this, you save it up, but you do this. You do not do this back propagation to a theta 2. You now do it here. So in this case, del theta 2, del will be, again, this is saved. So we will save till this point of time. Okay. This will be saved. Not this. This will be saved. That's how you save in the computer. But now the next part will be del H2. H2 is also a function of A1, right? A1 times del A1 H1 times del H1. Now theta 1 comes. Right? So you save it up here. You save this thing up here. And this is new. So you do not do this again. You save it up. Okay? That's why it's so beautiful. Understand this very carefully. So this is all about it, guys. This is all about what is backpropagation. So this whole thing, how it's done under called AutoGrad. Okay, in PyTorch. That's its main, like one of the core contribution of PyTorch. Or for this backpropagation is not easy because understand there are millions and millions of parameters. How to do it together? That's the most beautiful idea. The way to do it together is define proper layers. For each one of them, you will have a theta back. Okay, for each one of them, you will have a theta back. And yeah, so this is the basic idea how it's done. Core idea. Did you understand, guys, why it's different from logistic and linear? Because this is how it's saved. It's backpropagated because it's we want to save what's happening till here, and then it's you keep it here, and then you backpropagate the rest of the part. Because H2 has two connections. Okay, this is why it's a bit complicated, but it's also beautiful to know, understand how it works. Does it make sense, Vivan, Anushka, Ahan, the idea? Any questions?
Yeah. That's it.
So if you observe, there can be many other ways of doing it. Sometimes in something called residual networks, we will see later on, the graph. So now you see this is a graph. This is a graph. Mathematically, it's a graph. We have nodes. So we have x, h1, it has theta. Essentially, you can see if, so the way to think about it is this. This is a graph, a special type of graph. There's no, yeah, graph. So let's see what it means. And people use the property of these graphs, of the graph to compute. For example, here you can see that whatever, so the idea is this graph formation is this. If f is a function of x1, x2, or xn, we write like this: x1, x2, xn. And then f. Okay. But when it's a vectorized format, you usually write as x because it makes vectorized format well. So we can say x f. Now, if you have other theta, let's say g of x comma theta, then you write x of g comma theta. The question is that how do you represent it? So ideally there are two things. One is how do you properly define the nodes? Okay. The way it's defined is input and parameters. There are two aspects. So sometimes what happens is that x, of course, f has theta, but let's say from previous some, let's do it like this. So let's say x1, then f, this has theta 1, let's say, or let's say it has no theta. And then another g, but this has theta. But this is not only theta, there is also addition here. People are adding here, like this. You can define it like this. To make it simple, you can define it like another addition function here. You can make it simple. Okay, so that you can backpropagate easily. You can make it in many different ways. You can add it like this. Okay, or you can add it like this. Two things are added here. So it makes a graph. Okay, so let's say there's an age, but here there is a theta 2, like this. Lots of layers. This is called something called residual stuff, which will, if you do computation, you will understand why it's useful. But there can be a graph like this. The goal is to find the final loss function and backpropagate and stop and save every at, like, keep on doing and save here. So save here and do it here, and then use that saved one to go back. Again, save here, and then again, there is no need to go back here because there is no theta. So just do it here, stop here, because you will already save it. So how is this important? This, you see that the first step is this. First step is, so this is what's happening. In the first step, you're actually finding the output here, every step. So that's feed forward. In the first step, so this is feed forward, feed forward and backward, feed forward and backward. So this, for feed forward, is when you propagate to find the loss. So you find x dot dot to find the loss, and backward is when loss is taken backward to find the theta 1, theta 2. Okay, the updates. So this is what's happening under in back propagation, guys. Okay, very simple, very elegant, and very beautifully done. And yeah, that's all about it, guys. That's all about back propagation. And tomorrow we will be trying to code it out, okay, for different functions, for different steps. And if we have time, we will try to build a simple structure for just a few given functions out there, okay, to see actually how it's happening. We will just do basic gradient descent. We will just code up, like we will assume just a few loss functions, few so you see that it depends on how to save it up. You see, this way to save it up is defining the proper loss function. So defining two things. To save it up properly, to make it elegant, we need a graph. And the graph consists of nodes and edges. So graph consists of layers, each function. So those layers are functions. So you can make separate functions, and each function has one gradient, back and forth, because it's dependent on that local gradient. So each function should have a gradient attached to it. And also not just the gradient, the feed forward. So what's happening here is x is going to f, input is going to f. So at f, there are two information. One is the output, what happens if it goes back. So output, like f of x. One is the derivative of that, the del f del. Two information. So this is the gradient information. So one is the backward, one is the forward. Two information are saved in that node. Okay. So it's very important to know how this is saved. So forward, so it's called output, and the gradient. Two information are stored in that. Every node, two information are stored. Okay. So the beautiful part is that you have to build the function. Say whenever you define a layer, say every layer has two information. So whenever you define a layer, you will have two separate functions. One is for output in that layer only. One is for gradient. So that it helps you backpropagate. The whole reason is that this backpropagation is local. Thanks to is local. Local means for each layer, for every layer, it happens. You can define it beforehand. So what helps? This helps in coding it out well. Okay? So we'll try to do it, but understand to do it, we need finite number of layers. And also loss function. Loss function is also a layer kind of, right? So it's a finite kind of layers. So we will try to define it so that it becomes easier. Okay. If we have time, we will try to code it out fully. And that we will also learn. I will pre-compute the derivatives because that's not so important. The important part is how to understand the structure. Okay. All of you understood it, guys? Yes or no? So
Yes, sir.
very good. So tomorrow, day after tomorrow, we will do this, and then once we do this, we understand how the gradients are processed. Then next class, it will be mostly about how to train it. Like we know all these things now. The training means we will use some data in action and see what happens. And the project will be about using a real data to use two ways. One is the challenging problem will be to use this method to find it, and the easier project will be there will be two projects. One is to use this method to find it, but I will give you the code so you can play around with it. And the second one will be using a real data and using PyTorch with existing functionalities to find the result and see and compare them. Okay, for a real data, but I will do it for a demo data. Okay, so that's what you have to do. Okay, got it, guys? Make sense?
Yes, sir. Yeah.
Okay, superb. This is exciting stuff, and I hope you enjoyed backpropagation. I will see you in the next class. Bye bye.
See you in the next class, sir. Bye.
Thank you.
Thank you. Okay, sir.
Bye.